Hi everybody, it's Mr. Johnson again. It's Sunday, September 13th. We just watched the Seahawks dominate the Atlanta Falcons. And man, did Russell Wilson look good today. Going to be talking with you today about section 1.3. So we're on page 31 of our book to begin with. And this is going to be about measurement, precision, and recording significant figures, significant data. I'm going to flip my page to, the next page where we see an image of some measuring devices. Over time, I hope to get you some virtual lab experiences. Of course, over time, I hope to get you in the actual lab for you to have your hands on some of these devices, but for now, we have to settle with this beautiful image. What this topic is all about is the fact that in science and in chemistry this year, we're going to be using numbers all the time. We're going to use numbers in problems. We're going to solve problems from numbers. We're going to record numbers, of course, for measuring devices as well. And the idea is that all of those numbers that we use have some uncertainty to them. And all of that uncertainty in those numbers ultimately comes from the measuring device from which they were obtained. And what you have to think about is that when you're solving a problem in your book, and it's asking you to calculate a density from a given mass in a given volume, you've got to assume that those values that were given to you in the book for the mass and the volume came from a measuring device, and the way those values were recorded and reported to you is based on the precision of that measuring device, how much uncertainty there is in it. And I'll talk with you about what I mean by that. So as we look at this picture here, we see that we've got a graduated cylinder here, we've got a burette, we've got a ruler, and then this is a pipette. Each of these devices, if we zoom in, has some incrementation on it. What you may not be able to see is that this graduated cylinder is incremented to the 1 milliliter. The smallest increments on there are 1 milliliter increments. This burette, which is a more precise device, and I'll talk more about that word in a bit, is incremented to the nearest tenth of a milliliter. And because those increments are smaller, it makes it more precise. This pipette is also incremented just to the tenth of a milliliter. So it would have the same degree of precision as would this burette. So what this is all about, this notion of precision and significant figures, is knowing what the increments are on the device and how those increments, and what those smallest increments are, contribute to the precision or uncertainty of that particular value. All right, so I've flipped to the next page. We're looking at the top here and at this definition of the word accuracy. In addition to a measured value having a degree of precision, which we'll talk more about in a moment, a measured value can also have a degree of accuracy. And accuracy, as we see up here, is how well a measured value agrees with the true value, how close a measured value is to the actual value, whatever that is. That doesn't have to do with the increments on a device, which again are about precision. It has to do with how well that device was made, how well it was calibrated, whether the lines on the device were in the right place to begin with. Or whether, if you're using a digital scale, you zeroed it, you taired it to begin with. If you don't, it's not very accurate. There's not a whole lot we can do to control accuracy. It's based on, again, how well that device was designed. And it's not something we focus on a ton in here. We assume that devices that we are using have a reasonably high degree of accuracy, and we then focus on the precision of that device and making sure we record the proper number of significant figures. We see down here, there are two definitions for precision. The second one being the definition that we will use more. The first one says that precision refers to how reproducible a measurement is, how close together several measurements come to each other. If, for example, using a graduated cylinder, you measure the volume of water 3 different times, and you get 10.0 milliliters once, 10.1 milliliters the second time, and 10.0 the third time, one could argue all of those measurements are close together, they fall within a small range, and that those, therefore, because they're close together, or they were reproducible, are fairly precise measurements. Again, how close together several measurements fall to each other is a measure of their precision. And that comes down to the measurer doing a good job every time, reading the device the same way every time. Again, that's not what we talk about as often when we talk about precision. The second definition, which is really what the rest of this section is about, is how exact a measurement is. And what that has to do with is how many significant figures we can get out of a measuring device. And I know I keep using that term, and I'm going to come back to what it means in a moment. Or how small the increments are on that device. Because how small the increments are is a measurement, or excuse me, is a measure of precision and will give us a certain number of significant figures. All right, so if we scroll down, I'm going to talk through this quick check with you. I want to mention that these comment boxes, which are now visible in this lecture but weren't in the last one, are an error. Somehow the publisher has these comments here. They're going to be gone, I think, next time, so we're just going to ignore them for now. Anyways, what quick check question 1 asks us is, which of these is likely the most precise? Ask yourself, what do you think that really means? When it's asking you what is the most precise device, what is it really asking you? Well, what it's really asking you is which of these devices has the smallest increments on it. What do those smallest lines on the device represent? And although you can't tell real well, this graduated cylinder, like a lot of graduated cylinders, has as its smallest increment 1 mil increments. Not sure about the syringe, but they tend not to have very small increments on them. Pipettes tend only to have 1 increment. They dispense a relatively small volume once. And this burette, as you heard me mention at the beginning of the lecture, has 1/10 of milliliter increments on it. Because it has the smallest increments, it's the most precise and would deliver, which I'll be getting to in a moment, the most significant figures from that measuring device. The least precise device would probably be this volumetric flask, because it has only 1 increment on it. And a volumetric flask is designed to measure out a specific volume of a liquid, fairly accurately, in fact. All right, I take us now to the next page, and we're going to look at this definition here. Range uncertainty describes via a plus or a minus what the maximum value for a measurement might actually be and what the minimum value for that measurement might be. If we, for example, use a graduated cylinder and we measure the volume of water to be 52.5 milliliters, but really it could be anywhere between 52.3 and 52.7 because we're estimating, and I'll talk about that in a moment. Then we could say that the measurement of that water is 52.5 plus or minus 0.2 milliliters, that it really could be anywhere within that range. When we make our measurements, we aren't going to express the range uncertainty. Rather, there's going to be an expectation that it's also always going to be plus or minus 1/10 of that very last digit. And I'll talk with you about what that means in a moment. And if we look here at 56.3 milliliters, that's plus or minus 0.1, what we would write if we were using this graduated cylinder is just 56.3. Because it is assumed that that very last digit, that tenths place, is always going to be plus or minus 1. That the lowest it might be is 56.2 and the highest it might be is 56.4. So again, if we wrote 56.3, unless we were to say otherwise, we'd assume that it is meant to be 56.3 plus or minus 0.1. So I'm flipping to the next page, scrolling up. And to make matters even more confusing, there's another type of uncertainty called absolute uncertainty. And we don't refer to this much either. Much like a moment ago you heard me say we don't refer to the range uncertainty because it's inherent in a measurement. Well, absolute uncertainty is exactly how much higher or lower a measured value is than an accepted value. So if we know what the actual value is for a measurement and we measure it, we could express how far away they are from each other through what's called absolute uncertainty. The way that we use this, though, is rarely by itself. Rather, it is within a calculation that we do quite commonly called percentage error. In the numerator of this equation is what absolute uncertainty is, which is the difference between a measured value and the accepted value. The order those are in is important because if the measured value is greater than the accepted value, that's going to be a positive value. If the measured value is lesser than the accepted value, it's going to be a negative value. What that will give us are positive percent errors or negative percent errors. So again, the numerator, if we were just to express the numerator, is the absolute uncertainty. But if you compare absolute uncertainty to the accepted value, then that's percentage error. And again, that's something that we commonly do in lab, is express how close our value is to an accepted value through percentage error. Once again, that percentage error can either be positive or negative, depending on whether the measured value is greater than or lesser than the accepted value. And if the measured value is greater, it's a positive percent error. It's greater than you'd expect. And if the measured value is lesser, then it's going to be a negative percentage. All right, so I'm going to encourage you to do this quick check on your own. And after you've done it, to come back to this video. So consider pausing this for a moment, trying the quick check on your own. And that's just 1 and 2 I want you to do. And then come back once you've done it, resume play, and see how you did. All right, so 1 asks us for the absolute uncertainty, which again is the difference between a measured value and the accepted value. Looks like a student finds the mass to be 2.57, so that's the measured value. And that the mass should have been, or the actual mass is 2.46. So we're going to go measured minus actual. We're going to go 2.57 grams. Always be in the habit of putting units in your work, in your solutions, minus 2.46 grams is 0.11 grams. So that's the absolute uncertainty, and it's positive because the measured value is greater than the accepted value. If we want to find the percentage error, then we take that value, which is the numerator in the percentage error formula, 0.11 grams, and divide it by the accepted value. So we're going to do 0.11 grams divided by the accepted value of 2.46 grams. And that ends up being 4.5%. And we'll talk about a little bit later why I rounded this to 4.5, but the answer is because it has the same number of significant figures as the number that was used in the problem with the least. But I'll come back to that in a moment. So I deliberately rounded that to 4.5%. All right, here we are on page 36. I just flipped the page, and I'm looking at the top of the page here, the section about significant figures. So we're finally going to get into significant figures. I find the concept of significant figures interesting. I love the detail, the nuance to it. It explains to me why we round numbers the way we round them. But I also want to acknowledge that it's pretty tricky. It's kind of abstract. And if this is something that never quite hits home for you, if it never quite makes sense, if you're never quite good at significant figures, that's fine. You can be highly functional in this class without really getting good at significant figures. So I just want you to be aware of that. All right, so if we look at the top here at what's highlighted, it says that when determining the correct value indicated by a measuring device, you should always record all of the significant figures, or Sig Figs, and I'll be calling them Sig Figs. Basically, you need to use a measuring device properly. And using a measuring device properly means that you record the right number of digits from that device according to a rule, which is the right number of significant figures. All right, well, what does that mean? The next statement says the number of significant figures in a measurement includes all of the certain figures plus the first uncertain or the first estimated digit or figure. What that's basically saying is you record all the numbers from the device that you're sure of, all the numbers the device gives you, and then you always estimate one additional digit or one additional figure. And all those numbers you've written down, all of the certain digits that you're sure of from the device, plus this one additional uncertain or estimated digit, are together referred to as significant figures. This is a little overlay here. When you see things in green, that means you can click on them, and up will pop a little box explaining a little bit more. In this class, the estimated digit, or the uncertain digit, and this is convention in science, it's not just this class, is for us going to be, or usually, 1/10 of the smallest increment on the measuring device. What we're supposed to do, and I'll model this for you in a moment, is imagine 10 invisible lines between the smallest increment on the device. So we're going to see these little green areas. These are called overlays, and those are things that I've put into the text for you to click on, and that tells you just a little bit more than what the book has in there. If we click on this, it's telling us that the estimated digit, the uncertain digit, or the very last significant figure, once again, is going to be 1/10 of the smallest increment on the measuring device. we're supposed to imagine that there are 10 evenly spaced invisible lines between the smallest increment, and we're supposed to estimate where our measurement lies on those 10 invisible lines between the smallest increment. And I'll show you what I mean by that right now. So if we were measuring the mass of something, and the device we were using, imagine this is like a three-way balance, is incremented to the nearest 1 gram. And how I know that is each of these lines is 1 gram, 150, 151, 152, 153, 154. The first thing you want to do when you look at a device is ask yourself, how is it incremented? What are those smallest increments? What place on the number line do those smallest increments correspond with? And again, it's the ones place. It's the ones place.
So if we were to picture 10 invisible lines between the 156 and 157 line, meaning I'm picturing 156.1, 0.2, 0.3, 0.4, 0.5, I would estimate that that arrow falls at 156.5, like the number above suggests. Maybe some of us, though, would think it's 156.4 if that value weren't already given, or 156.6. Which is why when we say 156.5, we're really saying plus or minus 0.1 grams to account for the range uncertainty, that plus or minus 0.1 gram.
So this number that's written, this value, has 4 significant figures. The first 3 are known. We know what the hundreds place is. It's 100 grams. We know the tens place. It's 150. We know the ones place. We are estimating the tenths place because that was not given to us. And that estimated digit, again, is a significant digit. I'm now going to take you to a few images off the internet of devices for us to practice this one more time. All right, so here we've got a ruler. Let's assume that the ruler is incremented in centimeters, that the unit is centimeters. We're measuring the length of this little piece of marble here. I'm not sure what it is. Again, the first thing to pay attention to when you're using a device is what is the smallest increment on that device. And it looks like the smallest increment is 0.1. That's 0.1, 0.2, 0.3, 0.4, 0.5. So it's the tenths place that is the smallest increment, the tenths. All right, next thing I do is write down all of the known values, all the values I know for sure from this device. Well, I know it's greater than 1, so I'm going to write down 1. And I also know that it's greater than 1.1, 1.2, 1.3. So I know, I'm certain that it's at least 1.3 centimeters. What I'm expected to do is write an additional value. This is the estimated digit, also considered significant, that comes from estimating 10 invisible lines evenly spaced between 1.3 and 1.4. And I would estimate that that is on the 6, or the 600ths line. So I'm going to say it's 1.36 centimeters. I could write plus or minus 0.01 at the end, because that last digit is the hundredths place. But we don't need to, because we know that that's what that means. So again, I'm estimating this at 1.36. There's 3 significant digits in that value, 2 that are known, the 1.3, and the third that's estimated, the 6/100ths. All right, here we've got a beaker with what looks like some water in it. We're going to figure out what the volume of this water is. First step is to ask ourselves, how is this device incremented? What are the smallest increments? Well, it looks like it's 20, 30, 40. So the device goes up by tens. So I'm going to know to the nearest tens place with certainty what the volume is. And I'm expected to estimate 1 place past that, to the ones place. So I'm imagining 10 invisible lines between 40 and 50. I'm imagining a little 41, 42, 43, 44 line. And I would estimate that this is at about 43. So I'd write down 43 milliliters. Again, 43 is really saying 43 plus or minus 1. Maybe it's 42, maybe it's 43, maybe it's 44. But we don't have to write that. Writing down 43 milliliters, again, implies plus or minus 1 milliliter. Now, if we were in class together, it's at this point that I'd send you to your lab stations and have a bunch of measuring devices back there and give you a chance to practice using those devices to record the right number of significant figures, but that's not possible right now. Hopefully we'll get to do that soon. Next thing we're going to talk about is if you're given a value, you didn't record it, but you're given it, in a problem, let's say, you need to be able to, from that number, figure out how many significant figures there are in it. And I'll talk about why later. Just accept that there's a reason. So if you're given a value, how do we know from a given value how many significant figures there are in it? Well, there's 5 rules we use. Our book only has 4, but this little overlay, this little box, talks about a 5th rule, which we'll address in a moment. The first rule is that all non-zero digits are significant. Any number that's not a 0 is a significant figure. That could make sense, or maybe should. If there's a number that's not a 0, it had to have come from a device. And if it comes from a device, it's significant. And that's really the rule of thumb here, is if these digits are coming from the device, they're significant. All non-zero digits are significant. 1 through 9, always significant. Then there's 3 rules about zeros, and there's 3 kinds of zeros. There's what are called captive zeros. Some people call them sandwiched. I'll mention why in a moment. There's what's called leading zeros, and there's trailing zeros. And there's a different rule for each of those types of zeros. Well, captive zeros, which are zeros that are between any 2 non-zero digits, are always significant. They're always significant. And if we look down here at this second number, 87.050, that 0 right there between the 7 and the 5 is a captive 0 or a sandwich 0, and it would therefore be significant. So is this considered a sandwiched or a captive 0 because it's between 2 non-zero digits, and it as well would be considered significant. These zeros would have to come from the measuring device. They just happen to be zeros. 1 out of 10 times a number will be a 0. Because if the 5 is significant, because it's non-zero, right? If the hundredths place are significant, certainly the tenths place are. Same thing up here. If the ones place is significant, that's the, 10,000th, maybe 100,000th, so is that significant. All right, leading zeros, which are zeros to the left of the first non-zero digit. I didn't say zeros to the left of the decimal. Rather, zeros to the left of the first non-zero digit are never significant. This rule is kind of tricky to make sense of. We're just going to accept it for now. Leading zeros, once again, are never significant. So if I look at number 1 down here, these 2 zeros, which are to the left of the first non-zero digit, they're to the left of that 9, are both considered insignificant. They're not significant figures. Both zeros are to the left of the 9. They're not significant. Leading zeros are never significant. Captive zeros are always significant. Trailing zeros, the third type of 0, are sometimes significant. They're only significant if there's a decimal clearly expressed somewhere in the number. All numbers technically have a decimal right after the ones place, but if the decimal's not written, trailing zeros aren't significant. Trailing zeros are zeros to the right of the last non-zero digit. So we've only got one trailing 0 down here in these 2 problems, and it's this 0 here because it's to the right of the 5, the last non-zero digit. And that trailing 0 would be considered significant because there's a decimal somewhere in the number. But if the number were just 87,050, oops, let me get my pen here, 87,050, that 0, which is still a trailing 0, it's after the last non-zero digit, would not be significant because there's not a decimal clearly expressed in the number. Of course, there is a decimal place there, but it's not written, and therefore this trailing 0 is not significant. And then there's this 5th rule that I've inserted through an overlay. I'm going to click on it. And what that says is that exact numbers that aren't coming from a measuring device, that have some degree of imprecision to them, but that come from counting, exact numbers that come from counting, or that come from equalities within the metric system. Like in 1 meter, there's exactly 100 centimeters. Exactly. If you're using exact numbers and calculations, they have what's considered an infinite number of significant figures. An infinite number of significant figures. What they'll never do is limit the number of significant figures that you put in your answer, which is what we're going to go to next, is how we use these in a calculation. So exact numbers that come either from counting or from conversions will have infinite significant figures. And as I solve problems with you this year, I'll be modeling for you regularly how to be thinking about significant figures. So don't worry if it's still not making quite great sense. And then before we flip the page, I just want to take a peek at this sentence here. What this is talking about is Another way to deal with significant figures is to always express numbers in scientific notation, because in scientific notation, there will never be leading zeros. There will always be a decimal somewhere, meaning zeros are always significant. So it's just a lot easier with the numbers in scientific notation to determine the number of significant figures. I would encourage you to do this first practice problem, to do 1A, B, C, D, and E, to pause your video right now, and then come back once you've done it and see how you did. All right, in 1A, we notice that all 3 digits are non-zero. Non-zero digits are always significant, so this has 3 significant figures. In 1B, that's non-zero, that's significant. That's non-zero, that's significant. That's a captive zero, so that's significant. That's non-zero, so that's significant. And then this is a trailing zero. But because there's a decimal, that trailing zero is also significant. So I've got a total of 5 significant figures in that number. All right, in 1C, these zeros are all leading zeros, so none of those are significant. They're all in front of the first non-zero digit. The 7 and the 5 are non-zero digits, so those are significant. And then this 0, which is trailing, is significant because there's a decimal in the number. So I've got 3 significant figures, the 7, the 5, and that trailing 0, because there's a decimal there. If I look at D, there's 3 significant figures there because the 1 and the 5, which aren't zeros, are significant, and then that's trailing, but because there's a decimal, it's significant as well. And then finally, in E, the 3 and the 4 are significant because, again, they're not zeros. But those 2 trailing zeros are not significant because there's not a decimal clearly expressed in that number. Again, technically there is 1 at the end, but if it's not written, those zeros are considered insignificant. So it's just 2. All right, the next thing we're going to do, and I'm going to do this with you as opposed to asking you to do it first, is to round a couple of these numbers to a certain number of significant figures. Because in a moment, when I teach you rules for how to round answers to either addition, subtraction, or multiplication division problems, one of those rules is to round to a certain number of significant figures. So if I'm going to round 2A to 3 significant figures, or if I'm going to round any number to a certain number of significant figures, I start at the end of the number and realize that I need to get rid of one or more of the figures that right now appear to be significant. Right now, there's 4 significant figures in that number. I need to get it down to 3. I'm going to be getting rid of the last significant figure. It's always the furthest to the right that we get rid of significant figures from. If the significant figure you're getting rid of is to the right of a decimal, you can just lose it. But you've got to use rounding rules. If I were to get rid of this number and it were a 6, that would round the 5 up to a 6, because 30.56 really rounds up to 30.6. So this one's going to just be 30.5 because a 4 is not 5 or higher. In B, we need to get rid of 1 significant figure because there's 4 right now and I need 3. Remember that leading 0 isn't significant. So I chop them off from the end of the number. I'm going to need to get rid of just this last digit here. But because it is a 5 or higher, that's going to round the digit to the left up 1. But then that, becoming a 0, is going to round this up to a 9. So the 5 goes away, it rounds the 9 up to a 0. That rounds this 8 up to a 9. And what I'm going to get is 0.290. All right. If I go to D, and I modify it first, because I want to do a slightly easier version of D before we do D. I'm going to turn D into 104. And I were to want to round D to 2 significant figures. Again, I acknowledge there's 3 significant figures to begin with, that I need to get rid of that last significant figure, the 4, and I am not happy with this modification I made. I'm going to get rid of this 4. I'm going to make it a 6. You'll see why in a moment. And I'm going to do the same thing, round it to 2 sig figs. So I need to get rid of that 1's place, that 6. Because it's a 5 or higher, when I get rid of it, it will round that 0, the 10's place, up to a 1. But what I can't do is just lose the ones place altogether. Yikes, that should be a 1. I can't lose that ones place altogether. Because if I do, the number 11 is 10 times smaller than roughly 106. So I make that ones place a 0. But because there's not a decimal clearly expressed in this number, it's insignificant. When I round 106 to two significant figures, it turns into 110. I leave the ones place as a 0, but it's insignificant because there's no decimal in that number. That's a little tricky. We'll get better as time goes on. If I do D as written, which is kind of like what I had before, 104, here's what happens. Well, I've got 4 significant figures right now. Non-zero, 2 captive zeros, non-zero. I need to get rid of the tenths place as significant, and I need to get rid of the ones place as significant, kind of like I did up here. But 104, when rounded, is just 100. It's not 110. It's just 100. So for a moment, I'm going to write it as 100. But the problem is that 100 as written has no decimal in it, and both of those zeros, which are trailing zeros, wouldn't be significant. And therefore, this only has one significant figure. Yet, for whatever reason, I'm being asked to round it to 2 significant figures. What you can do, in some cases, is put the decimal at the end of the number, which is always there, but by writing it, you're making those zeros significant. By putting that decimal there, this now has 3 significant figures. But the problem is it's supposed to only have 2 significant figures, not 3. So I can't do that. I can't put that decimal at the end. If I had been asked to round it to 3 significant figures, I could have. My only option in a case like that is to use scientific notation, to express the number 100 in scientific notation, but with 2 significant figures. The number 100 in scientific notation is 1 times 10 to the 2. Well, how could I write that with 2 significant figures? Instead of writing 1, I could write 1.0 times 10 to the 2. So every once in a while, and this is about as tricky and nuanced as Sig Figs get, every once in a while, the only way to express a number with the proper number of significant figures is to use scientific notation. All right, so what's this all about? Why do we care about Sig Figs, other than that they sound cool to say? Well, one thing to care about is that we want to make sure that when we're looking at a measured value, we know how much uncertainty there is in it, what kind of a device it came from, how precise was that measurement. And that can really matter to a scientist when they're using that number meaningfully. The other point of this is that we do lots of problems in this class. We're going to divide numbers by each other, multiply, add, subtract. And what we need to make sure of is that the answers to those problems, which in theory came from measured values, don't have any more uncertainty to them than did either of the measured values. The answer to a math problem can't be more precise, can't have way more decimal places than either of the numbers we used. And one thing that always annoyed me in math was this arbitrary rounding of numbers. Well, this is now the first time you get to non-arbitrarily round, hopefully. All right, so the rule about multiplication division is that the answer to a multiplication division problem should have only as many significant figures as the number that was used in the problem with the fewest significant figures. All right, so we're going to go to the next page and practice this rule. The answer, again, to any multiplication and or division problem should have the same number of significant figures as whichever number was used in the problem with the fewest. All right, scrolling up. And let's use quick check number 3 first. All right, so we're going to take 0.054 grams and divide it by 1.10 seconds. 0.054 divided by 1.1, and I get 0.04909. There's another 0 9 in there. It's a good habit to begin with, or forever, to first publish your answer with more significant figures than you need, and then to round it. so that I know, or an evaluator knows, whether or not it was a math error or a rounding error, and we treat those differently. The unit is important. When you divide grams by seconds, you get grams per second. It's kind of a weird unit, but whatever. And we now want to round the answer to have the same number of significant figures as whichever number that was used with the fewest. So I look at the two numbers that were used, and 0.054 has only two significant figures because the leading zeros are not significant. So that's just got two significant figures. 1.10 though has three because the two ones, which are non-zero digits, are significant, and the trailing zero because there's a decimal and the number is. So that's got three. 2 is fewer than 3. 2 is the fewest significant figures of any number used, so I need to round my answer to two significant figures. So I work my way from left to right in the number until I get to my second and last significant figure, and that's the final one I will publish. These leading zeros are not significant, so they won't count. I'm going to need to write them. The 4 and the 9 will be my only two significant figures. Since to the right of the 9 it's not a 5 or higher, I don't need to round the 9 up. And since these numbers are all after the decimal, I can just get rid of them. So it's going to be 0.049. Oops, that's not very nice. 0.049 grams per second. That looks like seconds over seconds, but it's not. Grams per second. All right, there we go. All right, we're almost done here, and I know I've kept you here for a while. So the last thing we're going to talk about in the last rule is about how we round answers to addition-subtraction problems. And it's different than multiplication division. In fact, it's not about significant figures. It is, but the way it reads, it looks like it isn't. Again, multiplication division problems, we round to the fewest number of significant figures, but addition-subtraction problems, we round to the fewest or smallest number of decimal places. That rule only works when both numbers have a decimal place, but in reality, if you're adding or subtracting numbers in science, the likelihood is they're both going to have decimal places. They'll both have come from a similar device. So, again, the answer to an addition-subtraction problem should have as many decimal places as whichever number that was used with the fewest decimal places. So let's practice that, and then we'll be on our way. All right, so I'm going to look at practice problem 1 here on the next page. I just flipped to page 39, and I'm going to first add 16.407 to 5.70. And I get 22.107. 22.107. And if I add milliliters to milliliters, I get more milliliters. So my unit is milliliters. All right, well, both numbers had a decimal place, so I can round to the fewest number of decimal places. 16.407 had 3, 5.70 had just 2, so my answer can have only 2 decimal places, which means this tenths place will be my last decimal place and my last significant figure. Since to the right of it, though it's a 5 or higher, I can't just lose the 7 and turn this into a 0. Rather, this will round up to a 1 because that's 5 or higher. So the final answer is going to be 22.11 milliliters. All right, we're going to have more time to practice this in groups tomorrow. That's it for today. Thanks for hanging in there with me. As I look at my timer, it's been 40 minutes. I hope that that's been a good use of your time. Take care.